So we're going to look at it applied to Gaussian mixtures. I think this is one that is probably our easiest to understand introduction to the EM algorithm, okay? Okay, so first, before we get into this, we have to talk about mixture models. And in particular, we have mixtures of Gaussians. The notation I'm going to use in my notes will differ from the notation used in the textbook, which I generally try to avoid, but it's the notation I'm going to use in the homework, and I think I've got like another tutorial file that uses similar notation, okay? The idea behind a mixture model is that your data can come from different populations, okay? So you basically have a mixture of populations, except your data is not labeled. This is still a clustering problem, okay? Data can come from different populations, but the data is not labeled, okay? Okay. So your observation, you don't know from which population it came, okay? So when you see an observation, to which population it belongs. Okay. And so X, our matrix X is our observed data. Okay. And so let's just say we're dealing, our populations will be bivariate Gaussians, okay? So we will say our data will be a mixture of bivariate Gaussians, okay? So this is what we have. And so we might have, so if we have a total of n observations, then X is an n by 2 matrix. Okay, and what we have is Z is the matrix of labels. Okay, except Z is hidden from us, okay? Z is missing or, not seen. So for example, let me so in the population, you might have, so this is x1 and this is x2. Okay, you might have a bivariate. And let me, so here's one normal model, and then here's another normal model, and that one looks terrible. This last loop is really hard to draw, guys. Okay, all right, well, anyway. So this is what we have, right? And so this might be the true Gaussian distributions. Okay, and I'm going to call how do I color this? Where did my color palette go? Here we go. Okay, so can I like? Oops, I don't want that. All right, so we'll have this one. So here's one, and then we've got this one over here, and then we've got. Okay, so anyway, what we have is we might say orange consists of I don't know, maybe 20% of the data. Okay, and then purple, is that purple or pink? Magenta, okay. Maybe this is 30%, and green will be 50%, okay? And it doesn't have to be proportional to the size of these circles or anything like that, okay? But we might say, you know, half of the data comes from the green distribution, or something like that, okay? So these might be the true Gaussian distributions, and this is the true mixing proportions. Okay, so our mixing proportions, we keep track of them using alpha, okay? Alpha sub k is basically the mixing proportion of component k. Okay. All right, and so basically you are, I don't know, you spin a spinner, right? And it might land on orange, purple, or green. So each data point that's generated from this, so to generate a data point, basically, you know, choose orange, purple, or green according to the proportions, the mixing proportions, okay? And then, and under the true distribution, so if alpha, if basically k equals 1, then we're at the orange distribution. And we would say the probability of x given that z sub 1 is equal to 1. So this means that x belongs to the orange distribution. And then we would have the we have theta sub k, theta sub 1. Theta sub 1 are the parameters that define this multivariate Gaussian, okay? So theta sub 1 is going to be a collection of mu sub 1 and sigma sub 1, okay? So these are the parameters that define the orange Gaussian distribution. So, you know, mu sub 1 might be equal to, I don't know, this is like 0, 1, 2, 3, 4, 5, 6, 7, 8, okay. Okay, it looks to be like mu is like 2.5 and 2.5. Okay, I don't know, I'm making stuff up, right? And sigma sub 1 is going to be a matrix, and there's like a little bit of not a whole lot, so maybe like 2 and 3 and 0.1 and 0.1 or something like that. And so each of these distributions has their own mean and has their own mu and has their own sigma, okay? But they're represented just by the single value theta. But this is like a common thing, to just say theta are the parameters that define that specific distribution, and depending on what it is, it could be, you know, multiple terms or just one term, right? So if you have a mixture of Poissons, then you just have the lambda term, okay? And in this case, we have a mixture of Gaussians, so we're going to have a mu and a sigma. Okay, and so each value is comes from one of these things, and so the total probability of getting x, some individual x, over basically all parameters, which is captured in capital theta. This is going to be the sum of basically from k equals 1 to big K, the mixing proportion of that particular distribution times the probability of getting x given the class to which it belongs and the parameters of that component. Okay, so this is mixing proportion of component K, and this is the, in our case, the probability density for class K given parameters theta sub K. Okay. Okay. So what we need to do is that, you know, we generate data using this. So we say, so to generate data, you randomly choose which component it belongs to, and then once you have that component selected, you randomly generate a value from that Gaussian normal, right? So generating the data is not too bad, right? So randomly select a component, and then randomly draw a value from the Gaussian distribution of that component. Is this part okay? Yes, question?
So for the sigma, k goes from 1 to k.
K goes from 1 to k. K is the number of components you have. Okay. Yes?
What is the matrix Z sub k?
So Z sub k is going to be an n by k matrix. So, yeah, okay. So Z sub k, Z, okay, well Z is equal to an n by k matrix. And so it will be like 0, 0, 1 if the first value belongs to the third component. And then 1, 0, 0 if the second belongs to the first component. Second value belongs to the first component. Does that make sense? All right, and so you have this a matrix of zeros and ones that that tell you to which component a value belongs. Okay. Oops. So is the generation of data okay? I don't know. Here, let me open. Go back 2 slides here. So let's say we have this. So this is the true thing, and then when you have a random sample, it might look something like this. Have okay, you might have something like this. And we want to perform clustering on a data set like this. This is completely unlabeled, okay? So, and we don't know if this data point belongs to the green or if it belongs to orange or purple or whatever. We don't know. But from this, we want to perform clustering. We want to form 3 clusters, okay? And k-means clustering does not perform well because k-means clustering uses the distance, the Euclidean distance, as a measure of whether it belongs in a cluster or not. And in this case, a value that's right here, okay, is more likely to belong to the green cluster than in the purple or orange clusters, right? However, according to k-means clustering, a value that's right here, based on distance, is more likely to be in purple than here's the center of orange, here's the center of green, and here's the center of purple. based on the distance, k-means will say this value is more likely to be purple than it is to be green. But looking at our distribution, if we feel like this point should be a green point, right? Okay, so the EM algorithm for Gaussian mixtures will take that into account, okay? And what we're going to do is the EM algorithm has an E step and has an M step, okay? The E step is for the expectation, so that's what the E, and the M is maximization. So E is the expectation step, the E step, and basically the result of the expectation step is going to be probabilities that each point belongs to a certain cluster. So this is going to be, we calculate the probability that each point belongs to a cluster, okay? This step, if you remember your Bayesian classifier, is very similar to the way the Bayesian classifier works, okay? Because the way the Bayesian classifier worked was that you give it the values, the input values, and what does it return? It returns a vector of probabilities that add up to 1. And it says what's the probability it belongs to class Setosa, and what's the probability it belongs to class Virginica, and what's the probability that belongs to class Versicolor. Here, you're going to get something similar. You do the E step, the expectation step, and it's going to calculate the probability that this point, given the input values, belongs to the orange cluster versus the purple cluster versus the green cluster. So we calculate the probability that each point belongs to a cluster. So you will have, this is given by the weight matrix. And what will the dimensions of the weight matrix be? It's going to be n by k. It's each point, and the probabilities, the row sums will all be 1, okay? N by k, each row is the probability of point n belonging to cluster k. Okay, so the row sums are all equal to 1. So that's the E step. Does that kind of make sense? All right. And so the probability for each value is going to be, the probability of belonging to a certain cluster K given the values of x of I and the theta parameters K. And this is going to be the likelihood times the prior divided by the marginal. Okay. And so the numerator is going to be the probability of x of I given z sub k and theta sub k. So this is just the normal multivariate normal density for that observation x of I. Guess it's each row is the probability of point I belonging to cluster K. okay, times the prior probabilities of z sub k equal to 1, okay, divided by the margin. I think we're going to have to continue this on Wednesday. Well, here, we'll get into the delving of all of this in a little bit more detail, the E step. But yeah, from a high level perspective, the E step is very similar to your Bayesian classifier. Okay, not the naive Bayes classifier, but the regular old Bayesian classifier, which works the same way without the naive assumption. After you complete the E step, you do the M step, which is called the maximization step. And what you're doing here is you update the parameter estimates for each cluster component. Based on the points, based on the observations that quote unquote belong to the cluster. So in the E step, you basically came up with not cluster assignments, but something similar to that, cluster weightings. You say, based on this point, I'm thinking it's got this probability of belonging to the orange cluster versus this probability of belonging to the purple cluster versus this probability of belonging to the green cluster. And it might be, and after that, you're going to say, okay, let's update the parameter estimates. So this is kind of like updating your centroids in k-means clustering. So in k-means clustering, you had new assignments, and you said, okay, I'm going to update where the centroid is based on these assignments. It's kind of like that, except it's not, you don't have pure assignments. It's not, this point definitely belongs to this cluster. It's, this point has a 95% probability belonging to this cluster, a 4% probability belonging to this cluster, and a 1% probability belonging to this cluster. So therefore, you update the center and the variance-covariance matrix by weighting each point accordingly. So the ones that have a high probability of belonging to that cluster get weighted heavily in determining where that updated, quote, centroid is. And then the ones that have low probabilities are weighted much less heavily, okay? And according to that, you are going to update the center, which is going to be the mean, and then you will also update the variance-covariance matrix, okay? It's called the maximization step because effectively you are trying to maximize the likelihood of kind of your weighted data. So update the parameter estimates for each cluster based on the observations that belong to the cluster. Belong is in quotes because we do not have strict assignments. Okay. Instead, we have, kind of probability associations. Okay, and so this is similar to updating centroids in k-means clustering. Okay, so the EM algorithm is kind of like taking the classification part of the Bayes classifier and combining it with the clustering part of the k-means algorithm, okay? And then you iterate back and forth. You say, all right, let's update my centroids based on my, quote, assignments, which ones belong to this cluster. You do that. Then you go back and you say, let's recalculate the probabilities that this point belongs to this cluster. You recalculate that. You update your assignments then. After you've done that, you go back and you update your parameter estimates. You update effectively what's the centroid and the covariance matrix, and then you go back and forth, iterating back and forth. This is the very first time I've explained it. Okay, I will do this again, or kind of delve a little bit into more details on Wednesday, and we'll try to get a clear understanding of the EM algorithm.